Okay, so I am Sunil Deshpande, and the topic that we are going to discuss today is Newton's laws of motion. I have selected a couple of problems similar to the ones which have appeared in the previous CET papers, and I have slightly tried to modify them or tried to share a few more ideas about those concepts involved in the problems. In Newton's laws of motion, the questions that are going to be asked are based on, like, say, free body diagram making, and then a couple of bodies connected by means of a rope and pulley arrangement or strings, and you are supposed to find out the tension in any one of them. And then you also need to know something about pseudo force, and then even third law also. So I have taken a couple of problems wherein I have tried to highlight all these things. So in tension, I have very clearly shown there in the problems that it is always represented by an arrow going away from the body. And about third law, I have reminded you people that action and reaction no doubt are equal and opposite, but they are always seen or found to act on two different bodies. If action is found on one body, the reaction is going to be found on some other body. And if the two forces, in spite of being equal and opposite, are shown to be acting on the same body, please remember that they are not going to form an action-reaction pair. And regarding the tension in the springs, because I have also taken a couple of problems based on springs, the force in the spring is going to be written as kx, and the work done is going to be given by the formula half k into xi square minus xf square, where xi is the initial configuration of the spring and xf is the final configuration of the spring, maybe compression or elongation. Fine? Okay, so let us see all the problems on Newton's laws and try to enjoy them. So this is a very simple problem on Newton's laws of motion. This is on third law, and I am very sure the students will always have a confusion about what is this action-reaction pair. And I think most of you will have definitely by hearted that particular law, that for every action there is an equal and opposite reaction, or every force is always associated with one more equal and opposite force. Let me read the problem for you. A block of mass m is placed on a table and is at rest. Normal reaction of the table is not equal to mg. Normal reaction is equal to mg and forms an action-reaction pair. Normal reaction is equal to mg but does not form action-reaction pair, and normal reaction is greater than mg. See, there is a small difference between this option and this option. Here he says it is just not equal to mg, means there is a choice for becoming more than mg also and less than mg also, but here he appears to be pretty sure that it is greater than mg. Fine? Okay, so see, you have kept the block on the table and it is at rest, and if it is at rest, according to Newton's first law, the net force acting on that block should be equal to 0, or else it would have accelerated, and neither it is accelerating upwards nor it is accelerating downwards, nor horizontally towards the right nor towards the left. Therefore, if it is at rest, then all the forces acting on the block taken together should be equal to 0, right? Which are the forces which are acting on the block? One is the weight of the block, which is acting vertically downwards on the table, and second is the normal reaction of the table, which is acting vertically upwards, and they should be balanced. Therefore, n should be exactly equal to mg. No doubt they are opposite, because one is vertically upwards and the other is vertically downwards, but they should be equal to each other in magnitude. Fine. So now if you start looking at the options, normal reaction of the table is not equal to mg is ruled out. Normal reaction is greater than mg is also ruled out, because in that case the body would have accelerated. Okay. So among these two, one says it is equal and it forms an action-reaction pair, and the other says it is equal but it does not form an action-reaction pair. I think these are the beautiful two choices among whom the correct answer has to be chosen. And let me remind you that action-reaction pair is always equal and opposite, but is never found acting on a single body. So here the normal reaction is also acting on the block and mg is also acting on the block. So in spite of being equal, they cannot form an action-reaction pair, because whenever you see two equal and opposite forces acting on the same body, please understand that they never form an action-reaction pair. If action is on one body, reaction is always found on the other body. So the correct option here is C. So there is one more on Newton's laws of motion. Let me read the problem. A balloon of mass m is descending with an acceleration a. So right now it is descending and the acceleration is a, less than g, doesn't matter. How much mass must be removed so that it starts moving up with the same acceleration? We all know very well that according to Newton's second law, F equal to ma is written. But I am very sure that students must be having this particular confusion as to which force has to be taken as positive while writing F is equal to ma. Let me show you with a very simple example here. So suppose there are two forces which are acting on a particle. This is the particle and one force is downwards and that is F1. Another force is upwards and that is F2. And you are planning to use Newton's second law here to write F is equal to ma. You must have seen teachers sometimes writing F2 minus F1 is equal to ma and sometimes F1 minus F2 is equal to ma. And naturally I think you must have got confused as which one is correct, or does it keep on changing just like that. So let me just tell you that it is always in the direction of acceleration that we consider the force to be positive. Now suppose this particle is accelerating upwards, we write F2 minus F1, and if it is accelerating downwards, we write F1 minus F2, because we are all habituated with writing F equal to ma and never F equal to minus ma. So always take the force in the direction of acceleration to be positive. Fine? Not in the direction of motion. If the particle is going upwards but it is accelerating downwards, we don't write F2 minus F1 is equal to ma. See, I told you the particle is going upwards, so its velocity is upwards, but the acceleration is downwards. And the best example for this is a particle which has been thrown vertically upwards. It might be going vertically upwards, but the force is acting downwards. So always take the force in the direction of acceleration to be positive. Now this problem also I think highlights the same thing. A balloon of mass m is descending with an acceleration a. So right now it is descending and the acceleration is a, less than g, doesn't matter. How much mass must be removed so that it starts moving up with the same acceleration? So now we want it to move upwards with the same acceleration by removing some mass. So what we will do is, initially we will consider F1 minus F2 is equal to ma. And what is F1 here? It is a balloon of mass m. So I will consider F1 to be mg. And what is F2? The buoyant force which is acting on the balloon. So I will take it as B. So mg minus B is equal to ma. Fine. So this is the equation that you are supposed to write when the balloon is descending with an acceleration. Now you have removed some mass and therefore the mass has become m1. So now I will write B minus m1 into g. You must have seen the change. Initially I had written mg minus B is equal to ma. After I removed some mass and the new mass became only m1, I have taken B minus m1g is equal to m1a. And that is because now it is accelerating upwards with the same acceleration. See, starts moving upwards with the same acceleration. So now after having solved these two equations, you get the value of say m1, right? Once you get m1, your answer is m minus m1. Fine, because m was the original mass, m1 is the present mass. He is asking you the mass you must have removed, so it is m minus m1. And if you solve this, you will get the answer A. There is one more problem here with the same message. Let me read the problem for you. A body of mass 0.05 kg is found to fall, right, with 9.5 meters per second square acceleration. See, it is falling and the acceleration is downwards. The opposing force of air on the body is to be found out. Acceleration due to gravity has been given. So, this is a very simple problem wherein only F is equal to ma matters, but how you write F is equal to ma is important. That opposing force which we are supposed to find out is say F, and it is acting in the upward direction. I hope you agree, because if the body is falling downwards, the opposition should be upwards, and we have decided to take the force in the direction of acceleration to be positive. Acceleration is downwards, and therefore, I will take weight to be positive. So, I will write the equation as mg, the weight of the body which is acting downwards, minus the opposing force which is acting upwards, which you want to find out, should be equal to mass into acceleration, right. G is given to be 9.8, acceleration is given to be 9.5, mass is given to be 0.05, and F is to be found. So, F is equal to m into G minus A. See, 9.8 minus 9.5 is 0.3, and 0.3 into 0.05 will be 0.015. So, that makes the fourth option perfectly correct. So, there is one more on Newton's laws of motion. A stone of mass 0.05 kg is thrown vertically upwards. What is the magnitude and direction of the net force on the stone during the upward motion of the stone? See, the beauty of the problem here is in asking you what is the force acting on the stone during the upward motion of the stone. That is just to confuse you, because you may all of a sudden feel that because the stone is still during its upward journey, the force may be acting upwards, right. But please do not get confused. The velocity is in the upward direction, the body might be moving in the upward direction, but the force acting on the stone will be in the downward direction. Fine. Right. So, and we have always decided to take the force in the direction of acceleration to be positive, as you have seen in the previous problems. Okay. So, upwards and upwards can be simply ruled out. Whatever is the force, see, we have still not decided about the magnitude of the force, but the direction cannot be upwards is for sure. That is a stone, it is moving upwards, velocity is upwards, but the force is acting in the downward direction. So, the option can be either this or this. Fine. Okay. Now, this is 0.049 newtons and this is 9.8 newtons. The force could have been 9.8 newtons provided the mass was 1 kg, because the acceleration due to gravity is 9.8 meters per second square. Therefore, you could have taken 9.8 newtons downwards provided the mass was 1 kg, but the mass is 0.05 kg, therefore, it should be 0.49 downwards. So, that is the answer. So, there is one more on rope and pulley arrangement. It is a very simple one. See, there is a system of 3 masses 1, 2 and 3 connected by a string. 2 and 3 have been connected by one string and 2 and 1 have been connected by another, passing over a pulley, right, as shown in the figure. Table is rough. So, the table on top of which the block number 2 and 3 have been placed is rough with friction coefficient mu. Find the downward acceleration of m1. So, what is the acceleration with which m1 is going to move? Fine, that is the question. So, as he has clearly asked you to find out the acceleration of m1, let us take it for granted that the system moves. And because all of them have been connected by means of inextensible string, the acceleration of 1 will be same as acceleration of 2 will be same as acceleration of 3. 2 and 3 have been connected by an inextensible string. Therefore, if 2 moves ahead, 3 has to also follow. 2 and 1 have also been connected by an inextensible string. Therefore, if 1 moves downwards with an acceleration, 2 should follow with the same acceleration. Fine? Okay. So, now what we will do is, to get that acceleration, I will look at the net downward pulling force and divide by the mass of the whole system. I will try to see the net downward force which is trying to pull the body 1 and see the opposing force, that is the frictional force acting on 2 and 3, and divide by the mass in order to get the acceleration. So, I will write the net pulling force as mg, which is acting in the downward direction, minus the frictional force acting on 2, which is mu times n, you can say n2 if you want, and mu 2 also, minus the frictional force on 3, which is mu 3 and n3. Fine? Okay. So, now why is that I have written mu 2 and mu 3 and n2 and n3 is, the friction coefficient between 2 and the table must be different, and the friction coefficient between 3 and the table can also be different. But he has given only one coefficient of friction for both the blocks. So, we can take m2 is equal to m3, and even the normal reaction of the table on 2 and the normal reaction of the table on 3 could be different, but because the masses are identical, therefore, the normal reactions should also be equal. Therefore, I can write the equation as mg minus 2 mu n. And the another thing that you can notice here is that n will be exactly equal to mg. Normal reaction is acting upwards, mg is acting downwards. So, you can write this as mg minus 2 mu mg. Fine. So, this is the net downward force, or you can say the pulling force, and if you divide this by the mass of the system, that is 3m, you will get the acceleration. So, if you simplify this, the answer that you are going to get will be the fourth option, third option. See, m gets cancelled, g can be taken as common. So, g by 3 into 1 minus 2 mu. So, C is the correct answer there. So, this is one more problem on Newton's laws of motion, but the difference that you will find here is a block of mass m is pulled along a horizontal frictionless surface by a rope of mass m. So, he has also taken the mass of the rope to be considerable. Usually what we do is, we always neglect the mass of the rope in comparison with the block that we suspend with the help of the rope, but here he wants you to understand what difference does it make if we consider the rope also to have a considerable mass. Okay. Further he says, if the force P is applied at the free end of the rope, what force is exerted on the block? So, through this problem, he wants you to understand the importance of the free body diagram. See, you have applied a force of P, but where? Not on the block directly. You have applied it on the free end of the rope. So, basically it is on the rope that you have applied a force. Who has applied the force on the block? It is the rope. Therefore, what force does rope apply on the block is to be found, and not what force have you applied on the block, because you have not applied any force on the block at all. Fine. So, it is ruled out that the answer is going to be P. Okay, but for that also I should have to give you a reason. See, you have applied a force of P on the rope, and the same force could have been transferred by the rope to the block also, but that will happen only when the mass of the rope is negligible. Had there been no mass of the rope which is to be considered, then definitely whatever force you apply at one end of the rope will be the force at the other end of the rope also. So, here what is the difference? You have considered the mass of the rope, therefore, the tension in the rope is going to be different from one point to another point. Fine. So, what we will do here is follow the same method that we had used in the previous one. I will try to see the net force and divide it by the mass in order to get the acceleration first. So, the force that you have applied is P, and the masses which are to be accelerated are capital M of the block and small m of the rope, and say this is the acceleration with which both will move. So, you get the value of A. Now, if the force applied by the rope on the block is F, then that should lead to the acceleration of that block. So, I will write F equal to capital M, the mass of the block, multiplied by the acceleration with which the block is going to move, which can be written as P divided by capital M plus small m. So, the force which the block is experiencing, or the force which the rope must have applied on the block, is m into P divided by m plus m, and that makes the fourth option perfectly correct. So, I hope you enjoyed the significance of this problem. Mass of the rope has been considered, and you can very clearly see that the force in the string will keep on changing from point to point. On one end of the string or the rope you have applied a force of P, whereas at the other end of the same rope the force which is transferred to the block is not P, it is m into P divided by m plus m. But both are going to move with a common acceleration, and that acceleration is A, and the force you have applied on the whole system is P, because the tension in the rope is going to be internal. Fine. So, D is the correct option.